Thank you for the introduction. In my presentation, I will show how we use correlative microscopy to understand the air stability of a 2D gallium layer confined between epitaxial graphene and silicon carbide. So to start, I will show how we fabricate this material. So we apply a method called confinement heteroepitaxy to fabricate these 2D metals and alloy. And in our method, we start with silicon carbide sublimation. So we sublimate the silicon from the silicon carbide silicon phase, and that will result with a monolayer graphene with a buffer layer still attached to the silicon carbide. And then we use a plasma cleaner to apply oxygen plasma process to the surface of the surface, and that will result with defects to the graphene. These defects will help to intercalate the metal to pacificate the higher energy silicon tantalum bonding, um, and it will result to detach the buffer layer and make a new layer of graphene as well. So this interface that contains covalent metallic and van bonding within around 2 nanometer, we call it a half van der Waals bonding, and with this method we could intercalate variety of 2D metals and alloys. For example, here 2D gallium and indium gallium alloy. So why is this interesting to us? So we find the enormous amount of second harmonic generation comes from this engineered surface due to this variation in the bonding, and our cooperators in Penn State University, they are exploring this material to perform as a surface enhancement Raman scattering to detect viruses, which are much way better than using, for example, CNTs based detection. So to employ this material into applications, the 2D metal should be air stable, mean not oxidized in air. And for this purpose, we believe that the graphene plays the key role for the air stability of these 2D metal. So before understanding the role of the graphene, I want to explore what are the surface challenges for these materials. So this is our 1 centimeter, 1 centimeter silicon carbide cones that has this material on the surface here. And if we look at it in STM, we can see this multi-feature surface which has lots of gray contrasts, and typically we apply field cross sections and aberration corrected TM to have site specific look at the structure of this multi-feature surface. And we explain this in detail in this paper. And we understand from this analysis that the gray contrasts here, they are representing the metal intercalation beneath bilayer graphene or trilayer of graphene. Whereas this variation of the graphene layers here is the reason of why this variation in gray contrast is SEM. However, the dark contrasts and the white contrasts, they are representing non-intercalated region, and for sure there is some particles on the surface that saturates the SEM contrast. So this surface is ideally ideal example to do OJ electron spectroscopy mapping, and our OJ mapping confirms these differences in the carbon intensity related to the number of layers of graphene. And we see also this gallium coverage correlated with gray contrasts as well. But what's interesting in this presentation, and we need to discuss it in detail, is the oxygen signal. So in this oxygen signal, especially point 2, we still see oxygen co-located with gallium. And that's a was repeatable when we did XPS as well. And we could find two types of oxygen that's mainly bonded to carbon and a minor oxygen signal bonded to gallium. So because we see particles on the surface, we could understand that this wide range of micro and nanoscale particles, they could be the reason of the oxygen gallium bonding. However, the presence of the oxygen in this analysis is actually a red flag to us, and it motivates us to further study this material to answer two main questions. So, in our first question, where does the oxygen signal comes from? We applied variety of microscopy techniques in cross-section view and plan view to understand that. So in our HADF images, we applied stem eels, and fortunately we can see here there is no oxygen co-located with the gallium, which is a good indication. However, there is oxygen signal in the top here. It could be co-located with the graphene, because we use oxygen plasma to damage this graphene before the intercalation. But also we see this, we use carbon coating in our FIB preparation, and we doubt that this oxygen comes from our FIB. But interestingly here we see in our HADF images two types of carbon. One of them has a very low intensity in the HADF. So to differentiate between these two carbons and make sure that the carbon with low dense HADF is from our material, so we did another sample where we applied our FIB coating to be platinum first without any carbon coating. And interestingly, we still see this low dense carbon layer on our surface, which means it's introduced on the sample before our FIB coating. And by looking at the bright field stem, we can identify even holes in these carbon layers. So we call it a low dense carbon because it's low dense. It has less density and it contains carbon and oxygen signal in eels. And we believe that the material we see in the OJ mapping. But we could correlate more blind view investigations to this, and when we applied atomic force microscopy for the height map and adhesion map, we can see clearly that in some terraces there is this worm-like shapes structure on the surface, and that's also correlated with what we see in SEM, in a high-resolution imaging SEM, where we still see these worm-like shapes. And it's more likely when we cut a FIB cross-section, we can find these low-dense carbon with the worm shapes in plan view in our cross-sections view as well. So to summarize from these experiments, we understand that there is a low-dense carbon layer that has oxygen and carbon, and it may come from contaminations inside the intercalation furnace, or it may be a damage graphene from the oxygen plasma process prior to the intercalation. But our 2D gallium, it's a pristine without oxygen oxidation. So I will go now to the second question. Can our 2D materials be oxidized in air with the graphene coating? And to answer this question, we applied approach that if we could peel our graphene from the surface, and we have this area that contains graphene and the other doesn't contain graphene, so we could take a fib cross section from this site specific to study our material after expose our peeled graphene area to air for a few days. And we did that for 20 days after scratching the surface with a tweezer. And we understand from our recent investigations that SEM contrast is very sensitive to the 2D gallium and the silicon carbide, and we could identify what are the surface depending on the charging in SEM. And we are interested to the area between the yellow and the green lines here, which we could identify that has a gallium with silicon without the graphene coating, because it has a contrast in between the silicon carbide and the graphene surface. So we identify this area as our region of interest, and we site specific this region, and we apply a fib cross section from this region to prepare this ramella. So in this ramella, we now able to correlate our plan view in SEM and cross-section view in STEM imaging. So there's plan view, cross-section view correlation. We identify where is our cross-section line, and we could identify features that help us to correlate that. And we can easily find the scratch edge here, where we can see wrinkled graphene with large height on the surface. And if we apply yields mapping here, we can even resolve the wrinkles in the graphene in the yields mapping. So now we understand where's our peeled and unpeeled regions. And when we look at the unpeeled region, we can see crystalline gallium epitaxial to the silicon carbide and covered by bilayer graphene in this case. And our yields analysis, it shows no oxygen within the gallium region. However, if we look at the peeled region, we see non-crystalline gallium with lots of this cloud-shaped gallium oxide, because when we did yields, we can see that the gallium is fully oxidized. And for sure, there is no graphene here because we already peeled it. So in this investigation, we understand that the graphene provides the structure and air stability for our 2D confined metals. So to conclude, I will just give a take-home messages. So basically, despite these oxygen signals that we see in XPS and OJ electron spectroscopy mapping, we could reveal that the 2D metal are air stable due to the epitaxial graphene throughout this correlative microscopy we applied. And we find that correlative microscopy is very useful when we apply it in plane view and cross-section view to better understand the origin of this local spectroscopic signal. So thanks for our funding organizations and all our cooperators, and I'm happy to take questions.